The quantum harmonic oscillator is the quantum mechanical analog of the classical harmonic oscillator. Because an arbitrary potential can usually be approximated as a harmonic potential at the vicinity of a stable equilibrium point, it is one of the most important model systems in quantum mechanics. Furthermore, it is one of the few quantum mechanical systems for which an exact, analytical solution is known. One-dimensional harmonic oscillator. Hamiltonian and energy eigenstates. The Hamiltonian of the particle is, where m is the particle's mass, omega is the angular frequency of the oscillator, x is the position operator, and p is the momentum operator, given by the first term in the Hamiltonian represents the possible kinetic energy states of the particle, and the second term represents its respectively corresponding possible potential energy states. One may write the time-independent Schrödinger equation, where E denotes a yet-to-be-determined real number that will specify a time-independent energy level or eigenvalue, and the solution, psi, denotes that level's energy eigenstate. One may solve the differential equation representing this eigenvalue problem in the coordinate basis, for the wave function x, psi equals psi, using a spectral method. It turns out that there is a family of solutions. In this basis, they amount to the functions Hn of the physicist's Hermite polynomials. The corresponding energy levels of this energy spectrum is noteworthy for three reasons. First, the energies are quantized, meaning that only discrete energy values are possible. This is a general feature of quantum mechanical systems when a particle is confined. Second, these discrete energy levels are equally spaced, unlike in the Bohr model of the atom, or the particle in a box. Third, the lowest achievable energy is not equal to the minimum of the potential well, but h omega 2 above it. This is called zero-point energy. Because of the zero-point energy, the position and momentum of the oscillator in the ground state are not fixed, but have a small range of variance. In accordance with the Heisenberg uncertainty principle, this zero-point energy further has important implications in quantum fields theory and quantum gravity. The ground state probability density is concentrated at the origin, which means the particle spends most of its time at the bottom of the potential well, as one would expect for a state with little energy. As the energy increases, the probability density becomes concentrated at the classical turning points, where the state's energy coincides with the potential energy. This is consistent with the classical harmonic oscillator, in which the particle spends most of its time at the turning points, where it is the slowest. The correspondence principle is thus satisfied. Moreover, special non-dispersive wave packets, with minimum uncertainty, called coherent states oscillate very much like classical objects. As illustrated in the figure, they are not eigenstates of the Hamiltonian ladder operator method. The spectral method solution, though straightforward, is rather tedious. The ladder operator method, developed by Paul Dirac, allows us to extract the energy eigenvalues without directly solving the differential equation. Furthermore, it is readily generalizable to more complicated problems, notably in quantum field theory. Following this approach, we define the operators A and its adjointer. This leads to the useful representation of x and p. The operator A is not Hermitian, since itself and its adjoint are not equal. Yet the energy eigenstates, n greater than, when operated on by these ladder operators, give it is then evident that A, in essence, appends a single quantum of energy to the oscillator, while A removes a quantum. For this reason, they are sometimes referred to as creation and annihilation operators. From the relations above, we can also define a number operator n, which has the following property. The following commutators can be easily obtained by substituting the canonical commutation relation, and the Hamilton operator can be expressed as so: the eigenstate of n is also the eigenstate of energy. The commutation property yields, and similarly, this means that A acts on n to produce up to a multiplicative constant n1, and acts on n to produce n plus 1. For this reason, A is called a lowering operator and a raising operator. The two operators together are called ladder operators. In quantum field theory, A and A are alternatively called annihilation and creation operators because they destroy and create particles, which correspond to our quanta of energy. Given any energy eigenstate, we can act on it with the lowering operator, A, to produce another eigenstate with h omega less energy. By repeated application of the lowering operator, it seems that we can produce energy eigenstates down to E equals -infinity. However, since the smallest eigennumber is 0, and in this case, subsequent applications of the lowering operator will just produce 0 kets, instead of additional energy eigenstates. Furthermore, we have shown above that finally, by acting on 0 with the raising operator and multiplying by suitable normalization factors, we can produce an infinite set of energy eigenstates such that which matches the energy spectrum given in the preceding section. Arbitrary eigenstates can be expressed in terms of 0. Proof. The ground state, 0 in the position representation is determined by 0 equals 0, and hence and so on, as in the previous section. Natural length and energy scales. The quantum harmonic oscillator possesses natural scales for length and energy, which can be used to simplify the problem. These can be found by non-dimensionalization. The result is that, if we measure energy in units of h omega and distance in units of square root h, then the Hamiltonian simplifies to while the energy eigenfunctions and eigenvalues simplify to where hn are the Hermite polynomials. To avoid confusion, we will not adopt these natural units in this article. However, they frequently come in handy when performing calculations by bypassing clutter. For example, the fundamental solution of h-it, the time-dependent Schrödinger operator for this oscillator, simply boils down to the Meller kernel, where k equals delta. The most general solution for a given initial configuration psi then is simply phase space solutions in the phase space formulation of quantum mechanics. The most widely used of these is for the Wiener quasi-probability distribution, which has the solution where and lane are the Laguerre polynomials. This example illustrates how the Hermite and Laguerre polynomials are linked through the Wiener map. N-dimensional harmonic oscillator. The one-dimensional harmonic oscillator is readily generalizable to n dimensions, where n equals 1, 2, 3. In one dimension, the position of the particle was specified by a single coordinate. In n dimensions, this is replaced by n position coordinates, which we label x1, xn. Corresponding to each position coordinate as a momentum, we label these p1, pn. The canonical commutation relations between these operators are the Hamiltonian for this system is as the form of this Hamiltonian makes clear. The n-dimensional harmonic oscillator is exactly analogous to n-independent one-dimensional harmonic oscillators with the same mass and spring constant. In this case, the quantities x1, xn would refer to the positions of each of the n particles. This is a convenient property of the potential, which allows the potential energy to be separated into terms depending on one coordinate each. This observation makes the solution straightforward. For a particular set of quantum numbers, n, the energy eigenfunctions for the n-dimensional oscillator are expressed in terms of the one-dimensional eigenfunctions is. In the ladder operator method, we define n sets of ladder operators, by a procedure analogous to the one-dimensional case. We can then show that each of the I and I operators lower and raise the energy by omega respectively. The Hamiltonian is invariant under the dynamic symmetry group U, defined by where as an element in the defining matrix representation of U. The energy levels of the system are as in the one-dimensional case, the energy is quantized. The ground state energy is n times the one-dimensional energy, as we would expect using the analogy to an independent one-dimensional oscillators. There is one further difference. In the one-dimensional case, each energy level corresponds to a unique quantum state. In n dimensions, except for the ground state, the energy levels are degenerate, meaning there are several states with the same energy. The degeneracy can be calculated relatively easily. As an example, consider the three-dimensional case. Define n equals n1 plus n2 plus n3. All states with the same n will have the same energy. For a given n, we choose a particular n1. Then n2 plus n3 equals n minus n1. There are n minus n1 plus 1 possible pairs, n2, n3. n2 can take on the values 0 to n minus n1, and for each n2 the value of n3 is fixed. The degree of degeneracy therefore is formula for general n and n, Gn being the dimension of the symmetric irreducible nth power representation of the unitary group U. The special case n equals 3, given above, follows directly from this general equation. This is, however, only true for distinguishable particles, or one particle in n dimensions. For the case of n bosons in a one-dimension harmonic trap, the degeneracy scales as the number of ways to partition an integer n using integers less than or equal to n. This arises due to the constraint of putting n quanta into a state ket where n, which are the same constraints as in integer partition. Example: 3D isotropic harmonic oscillator. The Schrödinger equation of a spherically symmetric three-dimensional harmonic oscillator can be solved explicitly by separation of variables. See this article for the present case. This procedure is analogous to the separation performed in the hydrogen-like atom problem, but with the spherically symmetric potential where mu is the mass of the problem. The solution reads: where is a normalization constant, a generalized Laguerre polynomials. The order k of the polynomial is a non-negative integer, is a spherical harmonic function, h is the reduced Planck constant. The energy eigenvalue is the energy as usually described by the single quantum number because k is a non-negative integer. For every even n we have e equals 0, 2, n minus 2, n, and for every odd n we have equals 1, 3, n minus 2, n. The magnetic quantum number m is an integer satisfying minus m, so for every n there are 2 plus 1 different quantum states, labeled by m. Thus, the degeneracy at level n is where the sum starts from 0 or 1, according to whether n is even or odd. This result is in accordance with the dimension formula above, and amounts to the dimensionality of a symmetric representation of SU. The relevant degeneracy group: harmonic oscillators, lattice, phonons. We can extend the notion of a harmonic oscillator to a one lattice of many particles. Consider a one-dimensional quantum mechanical harmonic chain of n identical atoms. This is the simplest quantum mechanical model of a lattice, and we will see how phonons arise from it. The formalism that we will develop for this model is readily generalizable to 2 and 3 dimensions. As in the previous section, we denote the positions of the masses by x1, x2, as measured from their equilibrium positions in 2 or more dimensions, the shear vector quantities. The Hamiltonian for this system is where m is the mass of each atom, and xi and pi are the position and momentum operators for the ith atom, and the sum is made over the nearest neighbors. However, it is customary to rewrite the Hamiltonian in terms of the normal modes of the wave vector rather than in terms of the particle coordinates so that one can work in the more convenient Fourier space. We introduced then a set of n normal coordinates qk, defined as the discrete Fourier transforms of the xs, and n conjugate momenta pi, defined as the Fourier transforms of the ps. The quantity knots will turn out to be the wave number of the phonon, i.e., 2 pi divided by the wavelength. It takes on quantized values because the number of atoms is finite. This preserves the desired commutation relations in either real space or wave vector space. From the general result it is easy to show, through elementary trigonometry, that the potential energy term is where the Hamiltonian may be written in wave vector space, as note that the couplings between the positioned variables have been transformed away. If the Q's and πs were Hermitian, the transformed Hamiltonian would describe n uncoupled harmonic oscillators. The form of the quantization depends on the choice of boundary conditions. For simplicity, we impose periodic boundary conditions, defining the Th atom as equivalent to the first atom. Physically, this corresponds to joining the chain at its ends. The resulting quantization is the upper bound to n comes from the minimum wavelength, which is twice the lattice spacing A, as discussed above. The harmonic oscillator eigenvalues or energy levels for the mode omega k are, if we ignore the zero-point energy, then the levels are evenly spaced at so an exact amount of energy h omega must be supplied to the harmonic oscillator lattice to push it to the next energy level. In comparison to the photon case, when the electromagnetic field is quantized, the quantum of vibrational energy is called a phonon. All quantum systems show wave-like and particle-like properties. The particle-like properties of the phonon are best understood using the methods of second quantization and operator techniques described later. Applications. The vibrations of a diatomic molecule are an example of a two-body version of the quantum harmonic oscillator. In this case, the angular frequency is given by, where mu equals m1 m2, is the reduced mass and is determined by the masses m1, m2 of the two atoms. The Hooke's atom is a simple model of the helium atom using the quantum harmonic oscillator. Modeling phonons, as discussed above. A charge, Q, with mass, m, in a uniform magnetic field, B, is an example of a one-dimensional quantum harmonic oscillator. The Landau quantization.